Very good morning, students. Today we are going to enter into the angle modulation, which is one part of analog communication and which you will be encountering as a questions coming from the communication engineering and get EC streams and maybe instrumentation streams, IN streams. Now, myself, Professor Satish Kumar Ganamaneni, Assistant Professor in Kids School of Electronics, and this is my mail ID gskf@redkit.ac.in. Those who are having any kind of queries, they may be mailing to this related to this topic what I am going to teach for the next for this class session. Okay, now going to my presentation outline. Today the different topics I am going to discuss are the definition of angle modulation. What are the different types of angle modulation? Okay, maybe the frequency modulation, then the phase modulation, which are in short called as FM and PM. Why these two are the types of angle modulation we'll be going to see. The relationship between both of them, the waveforms, the comparison of NBFM and WBFM. Here NB stands for narrow band, where WB stands for wide band FM. Then the different types of generations of FM we'll be going to see, how the FM can be generated, how the FM may be detected. One of the very important thing is phase local loop here. Coming to the generation, the important thing which is coming in your previous gates also, maybe the concept related to the Armstrong method. Then FM super heterodyne receiver, where you will be studying how you are able to receive the signals, why it is a super heterodyne receiver, what are the intermediate frequencies for the FM, maybe roughly around 10.8 megahertz. Okay, then what are the other things and what kind of problems may be coming to you maybe in your gate or some engineering services examinations related to communication stream. These are all the things what we are going to discuss for today's class. Now basically going to the definition, the basic definition of an angle modulation is, this is the definition of what? Angle modulation. Our current topic is what? Angle modulation. Now going here, what is the name suggesting you angle means? For suppose if you have taken a certain carrier signal like this, S of t equal to AC cos theta of t. Here AC is representing you the amplitude part, then theta t is representing you the angle part. Now how can the angle may be further subdivided? The angle may be further subdivided into two different things which you can express here, 2 pi fct plus phi of t, where fc stands for the frequency of the carrier, then phi stands for the phase of the carrier. Now that's why the angle modulation may be of two different varieties. What are the two different varieties? You can now categorize them into two different things. One is the frequency modulation, the other one is a phase modulation. And from your earlier module you might be knowing what is the definition of a modulation. It is a process in which certain parameters of a carrier wave will get varied with respect to the instantaneous values of the message or the baseband signal. Now here which property of the carrier wave is getting varied? Angle property is getting varied. With respect to what? With respect to your message or baseband signal. Now this is the basic carrier signal S of t. Now, and the basic properties here, AC represents the amplitude, FC represents the frequency, and phi t represents the phase. And our current point of discussion is angle modulation. That's why here two parameters are there. One is a frequency parameter, the next one is a phase parameter. Now, going into our next topic. Yeah. Before studying anything, how will you define the instantaneous frequency of any waveform? The instantaneous frequency is defined as the rate of change of phase for every 2 pi radian interval of time. What I mean here to you means, for suppose you are having a certain signal like this, maybe your S of t. Now, cosine signal I am mentioning here, you are having a signal like this. This is your S of t for suppose the carrier signal for the current case, and you know the basic phases at different points. The phase at this point, if it is 0 degrees, the phase at this point will be 180 degrees. This point again 270, this point is 90 degrees. This is again 360 degrees, or which is your 2 pi radians. Means whenever you are moving from here to here, you know that you have completed one time period, which is inversely related to the frequency. Now here, how can you define the frequency? Means the phase is getting changed from 0 to 360 degrees, and the similar thing is getting repeated over a periodic signal. For only periodic signals you can define the time period for which you can define the frequency. That's why how can you define your frequency here? It is defined as the rate of change of phase, and the phase is changing by how much amount? It is changing by 2 pi radian in one time period, or otherwise the instantaneous frequency can be defined as the change in phase with respect to time, and the maximum change is 1 upon maximum change is 2 pi. That's why the instantaneous frequency you are defining it as 1 upon 2 pi d theta by dt. Or here if you want to express also, you can simply write here 1 upon 2 pi. The change in phase is how much? 2 pi minus 0. And change in time is how much? T minus 0. Now is your, for a particular case, is your f is equivalent to 1 upon t or not? 2 pi getting cancelled. Yes, that's why you can take this definition as fi of t, the instantaneous frequency of any signal. Whenever you are given with an equation, you can calculate it like this: 1 upon 2 pi d theta by dt. Now, going to the current case, if you see here, theta is 2 pi fct plus phi of t. That's why the instantaneous frequency can be calculated as 1 upon 2 pi d by dt of 2 pi fct plus phi of t, where phi of t is the phase, theta is the angle, fc is the frequency. Since you know the differentiation of t with respect to t is 1, differentiation of 2 pi fc will become 2 pi fc by 2 pi is fc you are left with. Then 1 upon 2 pi is getting carried here. Then differentiation of phi of t with respect to t is d phi by dt. This is how you will calculate the instantaneous frequency, on which many problems may be coming in GATE examination or engineering services examination. Now, let us try to find out the peak frequency deviation here. What is this deviation means? Deviation means certain thing which is deviating from a fixed value. Here fc is a fixed value. Okay, fc is a fixed value, but whereas this 1 upon 2 pi d phi by dt, which is going to get changed. That's why till what maximum value it can get changed, that is defined as the peak frequency deviation, which is represented by del f max. How to arrive at del f max? Obviously it is the maximum of change of phase multiplied by 1 upon 2 pi. That's why 1 upon 2 pi d phi by dt maximum. Now, in a similar manner, if you want to find the maximum phase deviation, this parameter is your phase. That's why the maximum of this you can calculate to arrive at your peak phase deviation. Hope everybody understood with the basic definitions of instantaneous frequency, peak frequency deviation, and peak phase deviation. We will be seeing certain problems, how we will be solving. Next, Coming to the types of phase modulation, types of angle modulation, there are two types which we have already seen. What are those two types? One is the phase modulation, the next one is a frequency modulation, and the current topic of discussion is phase modulation. Now if you can go back here, the definition is same. Here the angle parameter of the carrier is varied with respect to the instantaneous values of message. Now coming to the phase modulation, which parameter is varying? The phase of the carrier is varied with respect to the message signal. That's it. If you know the standard definition of modulation, then here in phase modulation, phase parameter of the carrier is getting varied with respect to the instantaneous values of the message or the baseband signal. Now how this can be mathematically expressed means, your phi t is kp times m of t, where m of t is your message signal, phi t is your phase, and kp is a certain constant. What this kp is called as means, it is called as the phase sensitivity. And if you want to know what may be its units, obviously we can simply apply here. This is in radians. Radians equal to kp multiplied with certain constant, some message, volts. That's why the units for kp may be of the form radian per volt, or maybe you may be calling it as degree per volt, whatever it may be. If m of t is a voltage waveform, if m of t is a voltage signal, until unless specified, m of t is always a voltage signal. Sometimes it may be current signal also. In that scenario, you may be expressing your phase sensitivity like this. There may be problems like that, radian per ampere. This is the case for what? If m of t is current signal. Until otherwise specified, always m of t is a voltage signal. If it is a current signal, radian per ampere, the units for kp. Now how can you express your phase modulated signal? S suffix pm of t stands for the phase modulated waveform, that is AC cos theta of t. Theta of t you have already seen. Theta is a combination of 2 pi fct plus phi of t, and you have already represented your phi of t as how much? You have already represented your phi of t as kp times m of t from the basic definition of the phase modulation. Now later we are moving to the, so much of calculations are given here. What are all these things? We are seeing one by one. For a single tone message, single tone means single frequency, a message of the form like this, am cos 2 pi fm t or am sin 2 pi fm into t, any sinusoidal signal which is having a single frequency component, that is called as a single tone signal, which is very easier for basic understanding. Now how you can express your PM signal? From this you can arrive at the next equation. S PM of t is AC cos 2 pi fct plus kp times m of t. Since you know your m of t is am cos 2 pi fm into t, you can express your S PM of t as AC cos 2 pi fct plus kp times am into cos 2 pi fm into t. Here you are getting some other parameter called as kp times am. There is the product of phase sensitivity multiplied with the amplitude of the message, which may be called as the modulation index for phase modulation, which is represented as beta suffix p. Beta suffix p represents the modulation index of phase modulation, which is written as kp times am, or in general it may be written like this, kp times the maximum value of the message signal. This is for any generic equation. This is for a specific equation. For a single tone, you know the maximum value of m of t here. The maximum here is, from this you can arrive at this, m of t maximum is how much? That is am. Why? Because you know the range for cos theta. Cos theta is always lying in between what values? The range is from -1 to +1. Obviously then cos 2 pi fmt range will be there from -am to +am. That's why here the maximum value of message is kp times am, which is called as the modulation index of phase modulation. Now if you want to calculate the peak frequency deviation here, That is simply equivalent to what? 1 upon 2 pi change in phase d phi by dt, which is kp times this one. 1 upon 2 pi d phi by dt. If you do, obviously what you are getting here, phi t is this one, d phi by dt will become how much? For here, if you want to take phi t, kp times m of t. That's why your phi t you can write it as kp times am cos 2 pi fmt. Now if you try to do 1 upon 2 pi, what is happening means I am using the next, oh yeah, here I am using your phi t is this value, that is kp times m of t. M of t means am cos 2 pi fm into t. Now how can you arrive at d phi by dt here, students? It's so simple. The derivative of cos theta is minus sin theta. Obviously what will happen here, kp am times sine of 2 pi fm into t, then derivative of 2 pi fmt will become how much? 2 pi, sorry, this is 2 pi into, this is not divided by, this is into. Then whenever you take 1 upon 2 pi here, it will come in the denominator later. Then you will be left with your 1 upon 2 pi d phi by dt as kp times am into fm. That's the peak frequency deviation for the case of phase modulation. Then what is the peak phase deviation? Obviously you know your phi t is what? Kp times mt. What is the peak value of this one? The peak value of phi t here you can be writing it as how much? Kp times am. That's why your peak phase deviation for frequency modulation is, for phase modulation is kp times am, whereas the peak frequency deviation for phase modulation is kp times am into fm. Okay, anyway we'll be solving problems on this, but before going to the problems you should understand the waveforms of both varieties, phase and frequency modulation. Now here if you observe the waveforms of the phase modulation, this is a message signal, plot 1 is a message signal, the plot 2 is a carrier signal. Obviously you know carrier frequency should be far greater than the message frequency. That's why you can observe time period of the carrier is very low compared to the time period of the message. Now I have used GNU Octave software for the simulations. I have just kept the same equation what you have studied, AC cos 2 pi fct plus kp times m of t, where m of t is your sinusoidal signal here, maybe cosine here in the current case. Then we are arriving at some plots like this, and if you observe in these plots there are some stretching or the lagging. Okay. This if you observe you are having some stretching, means whenever at this point, whenever the waveform is trying to decrease, at this point you are having the lagging phase, the phase is getting lagged. Why? Because the amplitude is going to get decreased. Whenever amplitude is decreasing, you know the basic funda that your phi t you are defining like this, kp times the m of t signal. Whenever m of t is decreasing, obviously what will happen, the phase is going to get decreased. That's why you are getting the lagging phase here. Whenever m of t decreases, phi t also going to get decreased. Now if we take the other one, now here I may be using maybe yellow, yes, whenever, yeah, if you can observe here, here the phi t, what is happening to the phi t means it is kp times m of t. Whenever mt is raising, obviously phi t will raise. That's why you can observe the corresponding lead in the phase. Whenever it is leading, obviously the waveform is more compressed. That's why whenever the message amplitude is going to get increased, you are having the leading phase. Whenever message amplitude is going to get decreased, you are having the lagging phase. This is about the waveforms of the phase modulation, how graphically you will be looking at them. Now we are moving to the another type of angle modulation. The second variety is the frequency modulation. Now, again the same definition, it is a process in which angle, which part of angle is going to vary? The frequency part of the angle is going to vary. And with respect to what? It is varying with respect to the message or baseband signal. And the basic definition is the instantaneous frequency is what is varying with respect to message, means instantaneous frequency is directly proportional to message signal, and where fc is the fixed center frequency or the carrier frequency, where kf is set and constant just like kp what you have studied in phase modulation. Here the sensitivity constant for frequency modulation is represented by kf, which is called as frequency sensitivity. And in general the units for this, if you are considering it as a voltage waveform, are, since these are in hertz, this is in volt, obviously the units must be of hertz per volt, until unless specified in the problem. For suppose in the problem if it is specified that if message is a current signal, if mt is a current signal, then obviously what should be happening to your units? Hertz per ampere. Why? Because if mt is a current signal, obviously your frequency kf should be having units of what? 1 upon current, and it should be giving hertz as the output. That's why hertz per ampere is a unit whenever if mt is a current waveform or a current signal. Now anyway, until unless specified, we will always consider your message as always as a voltage waveform. Why? Because any electrical networks, 90% of the cases you are trying to measure only two parameters, either the current or the voltage, and until unless specified whatever you are measuring you may treat it as in communication as voltage waveform. Then going to the equation for the FM, that is of the form AC cos theta of t. You know about theta of t from our old definition of instantaneous frequency, that Fy is 1 upon 2 pi d theta by dt. Now, and you know in the current case how you arrive at theta of t from here, means you just take 2 pi Fi of t, your 2 pi Fi of t is becoming how much? D theta of t by dt, from which if you arrive at theta of t, your theta of t should be equivalent to how much? It should be equivalent to 2 pi times Fi of t dt minus infinity to t Fi of tau d tau. Okay, both variables should not be same. If you use the Fi of t substitute with this equation, you will be left with what? 2 pi times Fc dt. Fc is a constant, Fc dt will become t. Then 2 pi is a kf is a constant, 2 pi kf times integral of minus infinity to t. Since till t you are integrating, you have to keep replace this one as some tau d tau. That's why here I have represented with certain other thing instead of replacing with t. You may keep it as x dx also, some y dy also, anything you may be keeping here. Now you have to replace this theta of t in the above equation. If you replace this theta of t in the above equation, you are left with your standard FM equation, that is the SFM of t is AC cos 2 pi FCT plus 2 pi kf integral minus infinity to t m of tau d tau, where m of tau represents your message signal and integral m of tau represents the integration of the message signal, where kf is the frequency sensitivity of the FM modulator. Now here also we'll be seeing with a case of a single tone message, and I already told you what do you mean by a single tone. Single tone means it is having single message frequency component, and it is chosen as AM cos 2 pi FM into T. Now if you chose this, obviously you can arrive at one thing, that your integration of MT dt or will be equivalent to how much? The integration will become equivalent to integration of cos is a sine signal obviously. That's why integration of cos is what? Sine 2 pi fm t. Then again here 2 pi fm, that's why it is getting multiplied with 2 pi fm. But here if you observe in this equation, AC is there, same AC you are dropping down. There is no change in AC. 2 pi fct you are dropping down the same. But here 2 pi kf is multiplied with this integration. 2 pi kf, whenever you are multiplying with this 2 pi will get cancelled. Obviously we will be left with kf times am by fm. Kf times am by fm, which may be represented with certain other parameter called as beta, where beta is the modulation index for what? Modulation index for your frequency modulation index, which is kp times am for phase modulation, and here it is currently kf times am by fm for frequency modulation. and integration of cos is sine. That's why obviously you are getting sine waveform here. But here your message is what? Your message is a cosinusoidal signal. You are having inside what? Integration of cos is sine. Then let us see the power in all the angle modulated signal. Before going to see the power, let us also look into the what is the maximum value of instantaneous frequency. And you have already been left with your Fi. The instantaneous frequency is how much? Fc plus Kf into m of t. From this equation you can arrive at the maximum instantaneous frequency as Fc is a constant, Kf is a constant. Whenever your message is maximum, instantaneous frequency is maximum. That's why your Fi underscore max it represents the maximum instantaneous frequency, which is Fc plus Kf times mod of m of t max. This mod represents the maximum value of m of t. And for a single tone signal, where you are considering your message signal as am cos 2 pi fm into t, for a single tone signal, obviously you know the maximum value of this message is how much? The maximum value is am, which is m of t max, which is a suffix m. That's why here kf times am is coming, and this kf times am is the extra parameter which is represented as del f. And what is this del f is called as? It is the extra deviation from the center frequency or the carrier frequency. That's why del f is called as frequency deviation, which is given down to you anyway. Now similarly you can calculate the minimum instantaneous frequency, that is Fi minimum is Fi plus Kf times maximum of minimum of m of t. Minimum of m of t here in the current case is minus am. That's why obviously it will become Fc minus Kf times am, which is Fc minus del f. And the difference between these Fi max and Fi minimum represents the total swing of the carrier. Swing means the carrier instantaneous frequency is varying in between Fi underscore minimum to Fi underscore maximum. That's why the difference between these two extremities is called as 2 times the del f, or 2 times the frequency deviation, which is called as carrier swing. Then already we have seen the modulation index of Fm, that is beta, which is Kf times am by Fm, or which is Kf times the maximum value of m of t by message frequency, where Kf is a frequency sensitivity, m of t is the maximum value of the message signal, then Fm is the frequency of the message signal. Hope everybody understood relating to carrier swing and modulation index. Now here let us try to find out the peak frequency deviation. Since this is your equation Fi equal to Fc plus Kf times m of t, peak frequency deviation will be equivalent to how much? The maximum value of Kf times mt. That's why Kf times m of t maximum, which is Kf times am. Hope with this also students are able to understand. Then going to calculate the peak frequency deviation, that is del phi max, which is phi of t max obviously. And you know in frequency modulation you have already seen the equation for the Fm, which I am giving again for you from our last slide, that is the SFM of t. What we have seen it like this, we have seen the standard equation like this: AC cos 2 pi fct plus 2 pi kf integration of mt dt. This is the integration from minus infinity to maybe t. This is, since this is in t, this will be tau, m tau d tau. Now what is the maximum value of the phase here? The maximum value of the phase here, if you can observe, that is the maximum of this value. That's what is being represented to you here: 2 pi kf times integration of m of t dt maximum. And the other parameter here what you need to understand is the power. Okay, what you need to understand here is the power, which I am erasing here for your ease. Yes, yeah. What is the power here, students? The power you are looking about only the amplitude is AC, and you know from the basic equation that whenever you are having an equation like this, for suppose C of t equal to AC cos theta of t, then the power in this signal, maybe some C of t, is equivalent to how much? The square of the RMS value, and the RMS value of any certain cosine signal is how much? AC by root 2. The square of the RMS value will become how much? AC square by 2. Okay students, have you understood how you are calculating the power? And since for PM also you are having at the same equation AC cos 2 pi FCT plus Kp times m of t dt, Kp times m of t, there also the amplitude of the carrier is remaining constant as AC. That's why there is no change in power of FM or PM, which is always AC square by 2, and the units are watt per unit resistance or watt per ohm. For unity resistance the power is AC square by 2. Means the one kind of conclusion you can observe here is power in FM is remaining always constant. But whereas if you are going to calculate the total power, maybe for AM, for suppose the power in AM, if somebody is interested in knowing the power in AM, that is we have already seen, maybe in your power in carrier plus 1 plus square of the modulation index by 2, which is the power in amplitude modulation, which is depending on the modulation index mu or m, whatever it may be. But whereas the power in FM and PM is independent of the modulation index. That is one of the takeaway from here. And next, going to the waveforms of the frequency modulation, the first plot represents your message signal, the second plot represents your carrier signal, and here also you can clearly observe your carrier frequency is far greater than your message frequency. Then the last plot represents your frequency modulated waveform, and here if you want to know at the lowest amplitude at this point the frequency is very high, or the time period, I may be noting down it like this: 1 upon fc minus del f, since the frequency will be very low. Why? Because the standard fi of t, instantaneous frequency, what you are studying, fc plus kf times m of t. Whenever m of t is negative at this point, very low, obviously the frequency is very less or the time period is more. Okay, which you can observe here also the same thing. Now if you are looking at the highest point, maybe I may be using green here for ease of understanding. Yeah, at this point if you observe, the difference is very less. Why it is very less? Why? Because your frequency deviation is very far positive. At this point the amplitude is more, obviously kf times the maximum value will be having here, which you will be arriving it as how much? fc plus del f, the instantaneous frequency. If the frequency is more, obviously time period should be very low. Whereas in the initial case, what is happening over here? Here you can observe that your m of t is minimum. That's why you are having the instantaneous frequency as fc minus del f. That's why here you are observing the more instantaneous frequency at highest amplitude of the message, and at the lowest amplitude of the message you are observing the low instantaneous frequency, or since the frequency deviation is negative you are having fc minus del f, which upon inversion it is a large value. That's why the time period is more. Hope everybody able to understand the basic difference between the waveforms of AM, FM and PM. FM stands for the frequency modulation, PM stands for the phase modulation. Now, there are certain problems here which we are going to solve for our ease of understanding. And here if you observe at this problem, always try to compare with our standard equation and you can arrive at so many other quantities. Our standard equation, maybe for single tone it is given like this: SFM of t is AC cos 2 pi fct plus maybe beta for ease of understanding for the current case of 2 pi fct, where the different, these are the things. And here if you compare, you can correlate your AC here as carrier amplitude as 7, then the carrier frequency fc as, from this if you observe, it is 20 times 10 power 6 hertz. Maybe since it is a voltage, if it is not given, you should be treating it as a voltage signal. That is, your carrier amplitude is 7 volts, carrier frequency is 20 to 10 power 6. If you compare with this, carrier amplitude is 7. Then here there are one sine and one cosine is there. Anyway, means it is of a form of certain thing where you are having a beta 1 fm1t, maybe certain other thing like this, some beta 2, some sine or cos, whatever it may be, 2 pi fm2t. Okay, now I'm trying to erase this. Yeah, means like this also the equation may be there. Okay, now in this case, if you try to see what they are asking you to determine, they are asking you to determine two parameters: maximum frequency and phase deviation. They are asking you to determine what? They are asking you to determine what is this f max, delta f max. Maximum frequency deviation is how much? Then maximum phase deviation, del phi maximum, is how much? For this you should know the basic equations. What are your basic equations? The basic equations are telling you what? Del f, how you are calculating? Del f is how you are calculating. Now del phi, how you are calculating? For suppose if this is your equation, your del f is the ratio of what? Del f you can calculate it very simply like that. You know your instantaneous frequency, that is 1 upon 2 pi d theta of t by dt. Now if you use the same formula here, how can you get your instantaneous frequency here? If you use the same formula here, yes, I need to summarize here itself. Okay, then if you put it in the same formula, your fi, you may be getting it as 1 upon 2 pi, then d by dt of 40 pi into 10 power 60, that will be equivalent to how much? 40 pi into 10 power 6, derivative of t is 1 itself. Then what is the derivative of sine theta, students? The derivative of sine theta is minus cos theta. That's why here you will be getting how much? 12 pi into 200 into cos of 200t. Then here derivative of cos theta is again sin theta. Obviously, then it will become how much? Plus 16 pi into how much? 200 multiplied with cos of 200t. Now here if you are going to observe, and if you are trying to simplify this fi, you are arriving at a 2 pi. If you cancel out here, you will be left with what? 20 into 10 power 6, that is a fixed center frequency. Then this is 6 into 200, that is 1200 cos 200t. Then this is again 8 into 200, that is 1600, plus maybe this is cos will become sine here. Yes, sorry, this is sine, this will become sine 200. Now here what they are asking you, del f max, what will be your del f max from this thing? Your del f max, how to calculate that one? The maximum value of this one, what will be the maximum value? The maximum value will be like this, that is under root of 1200 square plus 1600 square, or if you take out common as 200 as common, you will be left with what? 200 as common, you will be left with 2 pi is getting cancelled here how much? 6 times. 2 pi is getting cancelled here 8 times. 36 plus 84. 88 are 64, 66 are 36. You are getting how much here? 86. Okay. This is 12 pi means 6. 6 here and this is 8 here. 6 6 are 36, 8 8 are 64. Sorry, this is 64. 64 plus 36 is 100. That will be 10. That is 10 means what is your maximum frequency deviation? Your maximum frequency deviation is 2000 hertz. That's your one answer. Now, going to the phase deviation. How to arrive at the phase? How you can arrive at the phase? Obviously, you know this phi is what? Your phi, how you can express? Fi you are expressing 1 upon 2 pi d theta by dt. Okay. Then d theta by dt, if you do, the maximum value of d theta by dt is giving you the maximum phase. Obviously, then here, if you are looking to the phase, what is happening over here? Your theta of t, your d theta by dt, what you have left with means your d theta by dt is 40 pi into 10 power 60. Then it is 2400 pi t, that is 12 pi into 200, that is 2400 pi cos 200 t. Then this is 16 pi into 200, that is how much? 16 twos are 32, 3200 pi into how much? Sin 200 t. Now if you want to find the maximum of this, what may be the maximum of this? The maximum of this will be how much? You know that this is 40 pi into 10 power 6. What will be the maximum of these two? If you can simplify, then obviously you will be getting what is the maximum phase deviation from here. Okay, it will be there in the form of what? It will be there in the form of, for suppose sine becomes 0, cosine becomes 0, or otherwise it is this is the ratio 2400 and 3200. That is maybe you can simplify this, the maximum value of this, that you will be getting the maximum phase deviation of v of t. Okay, like this the problem may be given. You can use the relationship of instantaneous frequency, which is fi is 1 by 2 pi d theta by dt, and the maximum value of d theta by dt will give you what? The maximum phase deviation. Then there is another problem here given to us. Now let us try to understand what is given here. An FM signal is given by V of t is equivalent to 8 cos 4 pi into 10 power 6 t, then 12 sine 8400 pi t. Now if you try to compare with this with your standard FM equation, which is telling you that AC cos 2 pi FCT plus beta sine 2 pi FM into t, if you compare with your standard equation, now here you can write down what are the given values. Your carrier amplitude is 8, your carrier frequency is 2 into 10 power 6 hertz for the current case, 8 volts, don't forget mention the units. Then the modulation index beta is how much? 12. Then your message frequency f suffix m is how much? 2 pi fm u equal to 8400 pi t. Then it is 4200 hertz. Now after you compare this, what are the different things asked for you? You need to understand. The first and foremost one, what is asked to you is the carrier swing. And from our discussions, we know that the carrier swing is represented by 2 del f. And what is the relationship between beta and LF? You know the basic relationship between the beta and LF. I am writing some of the relationships here. That is, beta is the ratio of frequency deviation to message frequency. That is one of the relationship. And the power in FM and PM, which is always constant, that is AC square by 2. Then the other thing is, yes, how the beta is related to frequency deviation. The frequency deviation may also be expressed as kf times the maximum value of message amplitude by the message frequency. This will be sufficient for our current problem. Now if you observe here, first you need to arrive at what? 2 times the del f. Now your beta is 12, which you know, which is giving you what? Which is giving you the solution for your problem 3. Your modulation index is 12 here. You are able to find out the modulation index as 12. Then what is the power here? Power in this FM? Your AC is 8, then 8 square by 2 will give you how much? 64 by 2, which may be 32 watt per ohm. Beta is unitless quantity. Then with respect to this beta, how can you arrive at your del f? Del f is beta times the message frequency. Since your beta is 12 and your message frequency is 4.2k, from here you can arrive at how much? 12 fours are 48, 48, 12 twos are 24, means it will be around how much? 50.4 kilohertz. That is your 2 del f is how much? That is 2 times 50.4, which is equivalent to maybe, yeah, 100.8 kilohertz. Power is done, modulation index is done. Now what is given in the problem 4? In the problem 4 or the subpart 4, it is given to you this: what will happen to all the above 3 if the message frequency is doubled and message amplitude is tripled? Means what are the extra things given to you here? Message amplitude, message frequency is doubled, means that my new message frequency is 2 times the old message frequency. Then my new message amplitude, the AM dash, is tripled, 3 times the old message frequency. Now what are the other different parameters that are going to change here? If you observe here, is there any change in power? Power remains always constant, there is no change. Obviously your 2 bit 2 remains same, you don't need to worry. Then what are the other changes you can observe here? Bit 2 remains same, you don't need to worry. Then is del f dependent on the amplitude of the message? Yes. That's why what will happen to your carrier swing? Your new carrier swing will become 2 times del f dash, which is 2 times how much time the message amplitude is going to increase? 3 times. That is 2 times of 3 times of old del f, or which is 3 times of your 100.8 kilohertz, which is here 24, then 300 means 302.4 kilohertz. That is a new carrier swing. Then power remains the same. Then what will happen to the new modulation index? The modulation index, the new modulation index beta dash is becoming what? The frequency deviation is tripled and message amplitude is becoming how much? Message frequency is doubled. That's why it will become how much? 3 by 2 times the old beta, and the old beta is 12. That's why 3 by 2 times 12, what will happen to this? 3 into 6, which is 18. Now hope everybody is able to get the answers for everything. 2 del f is 100.8, whereas here 302.4. Power in FM is, in both cases it remains the same, that is 32 watt per ohm, since there is no change in amplitude of the carrier. But there are changes where? There are changes in frequency. Frequency of the message is going to get doubled, means new message frequency is 2 times the old message frequency. Then new carrier amplitude is getting tripled, 3 times the old carrier amplitude. Sorry, this is 3 times AM. That's why here del f is becoming how much? Del f is becoming 3 times kf times AM, which is 3 times the old frequency deviation, or your new carrier swing is also getting tripled. But whereas there is no change in the power, and also your new modulation index, which is depending on both the amplitude of the message m of t max and also on the frequency of the message. Amplitude is tripled, frequency is doubled. The new modulation index will become 3 by 2 times of your old modulation index. Okay students, like this the problem may be given, some problem. Now we are going to see the basic relationship between the phase modulated signal and the frequency modulated signal. Whenever you are having your message signal, you know the standard equations for your FM and PM. Again, once I am reiterating here, PM signal is of this form: AC cos 2 pi FCT plus beta means that is KP AM M of T. M of T means cos 2 pi FM into T maybe. Whereas if you go for the FM signal, it is of this form, which is AC cos 2 pi FCT plus 2 pi times kf times integral minus infinity to t m tau d tau, and this is kp times m of t, this entire thing. Now here if you observe the basic difference between these two, here you are having the modulation kp, frequency phase sensitivity, is multiplied with messages for the case of the phase modulated signal, but whereas for the case of the frequency modulated signal, your frequency sensitivity is getting multiplied with integration of the message. That's why it's very simple. The basic relationship between either of these things is, whenever you are passing your message empty, then whenever you are passing it through a differentiator, obviously you will be having m tau d tau minus infinity differentiator. Sorry, if it is a differentiator, yeah, your output will be of the form of derivative of m of t by dt. That is dmt by dt. Now if you are passing it through a frequency modulator, here you can arrive at the equation, and if you arrive at the equation here, it will be of the form AC cos 2 pi fct plus 2 pi kf times integration of derivative will give you what? Mt. Now here if you observe, what will be, if you compare with this your standard PM equation, your 2 pi times kf will be equivalent to your kp, that is your phase sensitivity, and this is a PM signal. Yeah, why? Because here the integration of the derivative of message is becoming message. Now in a similar manner, let us try to analyze the other one, which is our second one, generation of FM using a phase modulator MT. Now whenever you are doing integration, obviously you will be left with minus infinity to t m tau d tau or mx dx, whatever it may be you may be using. Now if you are passing it through a phase modulator, what is your phase modulated signal? That is AC cos 2 pi fct plus kp times m of t. What is your m of t here? That is minus infinity to t m tau d tau. Now is it approximating your FM signal or not? And if it is approximating, so what is the relationship between your kp? Your kp is getting equivalent to how much? Your kp is getting equivalent to 2 pi times kf, or otherwise whenever you are given with a phase modulator whose kp is known, how to arrive at kf? Kf is kp by 2 pi. And here also if you are given with a frequency modulator having known kf, how to arrive at the phase sensitivity of the PM signal? 2 pi times kf. That is the relationship between kp and kf, or the basic relationship between phase modulator and frequency modulator. Now going to the types of the frequency modulation. If you are going to the different varieties of the frequency modulation, as we have seen from the graphs that both the FM and PM are almost similar, except very one small thing. What is that small thing? Means their integration of message is there, here direct message is there. Okay, now let us try to see here the different types of the frequency modulation depending on what? The modulation index. Or suppose if the modulation index is far less than 1, in that case let us try to see how your FM signal will be there. This is the equation of a single tone FM, that is AC cos 2 pi fct plus beta sin 2 pi fm into t. And all of you are knowing the basic thing, that is cos of a plus b. From your basic mathematical skills, that what is cos of a plus b? Cos a into cos b minus sin a into sin b. The same thing I am doing here. Cos of, this is my a and this is my b. Cos of 2 pi f ct, cos of beta sin 2 pi fm into t, then ac minus ac sin of 2 pi f ct, sin of beta sin 2 pi fm into t. And the other important parameters here are, you know, the integration for the limiting calculations. Limit theta tends to 0, we know this sin theta by theta is 1. And the other important thing what we have studied from our calculus is that limit theta tends to 0, what will be your cos theta tending to? Cos theta is also tending to 1. Sin theta is tending to theta, whereas cos theta is tending to 1. That's why here cos of this entire thing has been replaced with 1, whereas sin of this entire thing has been replaced with the theta. Why? Because here your beta is far less than 1, then beta sin theta will be far less than 1. That's why here it has been represented here. Cos of this is represented as 1. Remaining things are one and the same. AC cos 2 pi fct, here AC sin 2 pi fct. And if you observe at this equation, if you want to further simplify, you can simplify it. Sin a into sin b. How can you simplify? Half sin of a minus b minus half sin of a plus b. Half cos, sorry, sin, two sin, product of two sines. Why? Because cos a plus b is cos a cos b minus sin a sin b. Cos a minus b is cos a cos b plus sin a sin b. Whenever you subtract cos a minus b with cos a plus b, you are left with 2 sin a sin b, or sin a sin b is half of cos of a minus b minus half of cos of a plus b. That's why minus of minus become minus of plus becomes minus of minus becomes plus, and you are left with AC beta by 2 on both sides. Cos of a minus b, here a is the highest point is 2 pi fct carrier frequency, the lowest one is 2 pi fmt. That's why you are arriving at this equation. Now if you want to observe how the plot of this will be there in spectral domain, we need to understand the spectrum for the narrowband FM signal. This is the frequency axis, this is 0. Then I am trying to represent you in form of the spectral representation for this narrowband FM. Now if you observe the first one, and our basic fundamental concept is this, we know that a naught cos 2 pi f naught t. From our signals and systems, you know what is its Fourier transform. It is a naught upon 2 del f minus f naught plus del of f plus f naught. That's why here if you can observe, you are having three cosines here, three simple cosines, and which are existing at its respective frequencies. Now first, if I want to plot AC cos 2 pi fct, I will be having two impulses, one existing at plus fc and the other one existing on the negative side at minus fc, and the amplitude of this is AC by 2. Why? Because a naught becomes a naught by 2. F naught means impulse existing at plus f naught and minus f naught. So plus fc and minus fc. Now if I want to plot the second one, which I may be representing with green here, this is minus AC beta by 2 cos of 2 pi fc minus fmt. Since it is negative, I will representing down, and it is existing at what frequencies? It is existing at fc minus fm on the positive frequency axis, and the negative frequency axis will exist at minus fc plus fm, and the amplitude becomes equivalent to how much? Minus AC beta by 4, or since I am representing it down, I may write it as AC beta by 4. Now for suppose if I want to represent the other one, which I am choosing this color, okay, this is existing at what frequency? Fc plus fm. Then obviously you will be having an impulse existing at what frequency? Impulses are existing at a frequency of fc plus fm, and here you will be having it minus fc minus fm, and again the strength of this impulse is AC beta by 4. From where you are getting the amplitude is this much, the amplitude of the impulse will become half of the current impulse amplitude. In the same manner, what we are going for AC beta by 2, half of the AC beta by 4. And here in the first case, if you are plotting the carrier signal existing at FC frequency, the amplitude become AC by 2. Now if you are looking at this spectrum, you can correlate it with the AM spectrum. Everything remains the same, and even if you want to calculate the bandwidth of operation here, the bandwidth can be simply given by this difference between these 2 points, which is the difference here is the bandwidth for narrowband FM can be mentioned as 2 times the message frequency, which is equivalent to the bandwidth of amplitude modulation. This is currently the bandwidth for narrowband FM. But narrowband FM and amplitude modulation are almost similar. But anyway, whenever beta far less than, it is of almost no use. This is only theoretically you are studying, and you may be using for generation of wideband. What is wideband means? Narrowband. Why it is called so? Why? Because it is having only two sidebands. What are the two sidebands? You have just now seen your two sidebands are your upper sideband and the lower sideband, just like what you have studied for your AM case. Only two sidebands are there. One upper sideband is there, one lower sideband is there. Bandwidth is very small. But let us go and look into the other variety, that is the wideband FM, where the bandwidth is increasing. How the bandwidth increase, all the other things has been discussed here, and the proof has not been given here directly. I am trying to represent you in form of the Bessel's coefficients. Bessel's coefficient. How this is related to the topic of spectral analysis of single tone FM. Single tone, that to wideband FM. Why it is called as wideband, we'll come to know from the end. Here if you observe the Zn beta is a Bessel coefficient, n lying from minus infinity to plus infinity, and here if you observe the amplitude is AC Zn beta at frequency Fc plus NFM into T. Now if you want to look at its spectral representation, for ease of understanding I am giving you here, and you will be having a similar spectrum on the negative side also. I am concentrating on the positive side. Negative side you will be having a similar spectrum, which I no need to draw for you. Then this one wideband FM I will be representing. We will be having so many amplitudes here. That's why please be very careful. Now one simple analysis from here is the coefficient of for n equal to 0. Okay, this will become Fc plus 0 into FM into T. That is the frequency. The amplitude is becoming AC Z0 beta. Then for n equal to some 3, what will happen to Fc plus NFM? Fc plus NFM will become Fc plus 3FM. For ease of understanding I am telling you. Then what will be the coefficient here? AC J3 beta. AC J3 beta. Why I am representing you all these things means, for suppose if you want to look at its spectrum, okay, I am plotting the spectrum here. Because of n equal to 0, you will be having one amplitude, and that amplitude is AC J0 beta. Since it is a cosine signal, you can be representing it as AC J0 beta by 2, existing at what frequency? Fc. N is 0. Now for suppose if your n equal to 1, then you will be having set another signal here. The amplitude will become AC J1 beta by 2. It will exist at what frequency? Fc plus FM. Now if you want to observe for n equal to 2, obviously you will be getting on the downside. Why you are getting on the downside, I will let you know later. The amplitude will become how much? Minus AC J1 beta by 2, and this frequency is Fc minus FM. Why? Because Bessel coefficients are having certain properties. What are those properties? Let me tell you in a very brief note here. Two big properties of Bessel coefficient are J minus n beta is minus 1 power n Jn beta, then summation n lying from minus infinity to plus infinity, Jn square beta is 1, from which you are getting the power in FMS constant always, and J minus n beta is J minus 1 power n Jn beta, from which if you observe for the third term, for suppose Fc plus 2 FM if you want to observe, then obviously you will be having at fc plus 2fm here. Here also you will be having, why I am representing on the positive side, I will let you know. The amplitude will become equivalent to how much? AC J2 beta or J minus 2 beta. Why? Because both are one and the same. From here if you observe, you keep J minus 2, it will be becoming how much? Minus 1 square J2. That's why J minus 2 beta and J2 beta are always one and the same. And the important observation what you need to do from here is, you will be having so on so far on both sides. And the other important observation is the difference between the consecutive sidebands is message frequency, and you may be calling the component here at USB 1. Okay, this is the carrier frequency n equal to 0. This is n equal to 1, USB 1. Then for suppose you are n equal to 2, what you will call that kind of thing? That is your upper sideband 2. Okay, like this, so on so forth. That's why theoretically if you consider, you are having infinity bonds on this side, infinite bands on this side, and also only on the positive scale. Negative scale also similar will be there. That's why the ideal, the theoretical bandwidth theoretical for FM is mentioned as infinity, or the bandwidth ideal bandwidth of FM is mentioned as infinity. But there is something called as practical bandwidth. What is that? We will be seeing. Means from here, what is the funda you need to take away means, at FC you are having an amplitude of AC J0 beta by 2, at FC plus FM AC J1 beta by 2, at FC plus NFM the amplitude is AC Jn beta by 2, the spectral amplitude, and the difference between the consecutive spectral points is FM. Now the practical bandwidth for the case of FM is given by a person named Carson, which is called as Carson's rule, which is the practical bandwidth for FM. By conducting experiments, he has arrived at this, and what he has arrived here is 2 times beta plus 1 into FM, where beta is a modulation index, FM is the message frequency. And if you can keep this equation, beta is equivalent to the ratio of frequency deviation to message frequency, you can arrive at the other equation, which is 2 times del F plus FM. Now here, going to the example 3, an equation has been, a problem has been given to you, and the problem given to you is, I am reading for your sake of understanding. A message signal is given by m of t is 3 cos 4200 pi t. The phase sensitivity is 11 radian per volt. The frequency sensitivity is 80 kilohertz per volt. Means from those things I can mention these things. The message amplitude is 3, message frequency is 2100 hertz. Why? Because it is 4200 pi t. Then the phase sensitivity, that is Kp, is given as 11 radian per volt, and the frequency sensitivity Kf is given as 80 kilohertz per volt. These are the things what are given to you. Now look at the problem once and try to see what the other has asked you to find out. Find the power bandwidth of FM and PM. If the message frequency is tripled, then determine the bandwidth. Now here if you observe, all these things, message signal is given, what they are asking you, power. Okay, then how you will arrive at the power means, AC you don't know, that's why the power here refers to what? The power in your message signal. That's why the power in your message, how can you give? Am square by 2, which is 3 square by 2, which is 4.5 watt per ohm for your message. Then you are asked to find what? Bandwidth of FM and PM. Then how will you arrive at the bandwidth for the case of the frequency modulation? Yeah, the bandwidth relationship is 2 times beta plus 1 into the message frequency. And what is your beta? Beta is del F by message frequency. And how will you arrive at del F? del f is your kf times the maximum amplitude of the message by the message frequency. Now from the problem given to you here, how can you arrive at these values? Kf is given to you as how much? 80 kilohertz, 80 times 10 cube. Then AM is given to you as 3. Then message frequency is given to you as 2100. That's why if you can simplify this problem, obviously you can arrive at certain thing, that is 240 100 by 21. If you can simplify this, that will be your beta. Then maybe 3 7 times it may go, then 3 800s, then 800 by 7 is your beta, or which may be 1 again 10, 10 means 1, then 30, 7 3s are 21, 7 4s are 28, then again 20, 20 means you can approximate it as 7 3s, okay, 114.3, okay, that is your beta. Now if you substitute in this equation, 2 times 114.3, that will become plus 1 will become 115.3 into message frequency is how much? 2.1, that's it in kilo. If you simplify this, you will arrive at your bandwidth for the case of the frequency modulation. Now here the other thing is given, PM we will see later. The message frequency is tripled. Now what is given to you here means they are trying to, this is related to bit A for FM, bit B for FM. Let us try to see. The message frequency is tripled, means whenever the message frequency is tripled means the FM dash is becoming equivalent to T times the message frequency. Is there any change in amplitude? There is no change. Then obviously there will be change in del F. Indirectly the change in the beta. Beta dash may be represented as how much? 3 times the volt frequency deviation by AM. It is not getting changed. There is no change in KF and AM. There is only change in where? Frequency of the message. That becomes 3 times, means beta dash is becoming beta by 3, which may be 800 by 7 3 is 21, or if you want to simplify this, 114.3 by 3, which may be roughly 3 3s are 3 4s are 12, 3 3s are 9, then 21, then 3 7s are 21, okay, 3 3s are 9 to 21, then again 21 it got cancelled, 37, then 37.13, 3 4s are roughly 12, okay, 37.4. If you try to keep in this equation, obviously you will arrive at your second answers. Your second answers will be 38.4 into message frequency. What is happening? 3 times the old message frequency, 3 times 2100. You need to simplify this to get your new bandwidth. Hope everybody understood for the case of the frequency modulation. Now let us try to do the same for the case of the phase modulation. Now if you look at the phase modulation, I am trying to write the same parameters over here. My amplitude of the message for the phase modulation, the amplitude of the message given is 3, then Kp phase sensitivity is 11 radian per volt, and the frequency of the message for you given in the problem is 2100 Hz. Now what they are asking in the case 1 means, in the case 1, if you go back to the problem also, 11 radian per volt, then message frequency is 2100. From this thing, message amplitude is 3. Now determine the bandwidth of PM. How to determine the bandwidth of PM? Simply, you know, the bandwidth is equivalent to what? 2 times the bandwidth of P plus 1 into the message frequency. You know about FM, and how to calculate the beta P? You know the beta P for FM is Kp times the maximum value of the message signal. Here Kp is how much? 11. What is the maximum value of the message? 3. That is beta P is 33. Then how can you arrive at your bandwidth now? You can arrive at your bandwidth using this equation. Bandwidth is equivalent to how much? 2 times beta P is how much? 33 plus 1 into message frequency is how much? 2100, which may be 34. 2s are 68. 68 into 2100. Or you can simplify this, 68 into 21, you are getting it as 68. Then again 8 2s are 16, 6 2s are 12, 13, that is 8, 12, 14, 28, or which may be 142.8 kilohertz. 142.8 kilohertz. This is about the case A. Now in case B, what it is being told, message frequency is tripled. Now you need to determine the bandwidth. Now case B I am mentioning here, what they have given you means FM dash is tripled, 3 times the message frequency. Then is there any change in beta P here, students? Beta P is depending on the amplitude of the message. There is no change. KP there is no change. AM there is no change. Beta P remains same. But what is happening to the message frequency? That is becoming 3 times the old message frequency. Or obviously your given value here is how much? 3 times 2100, which may be 3 to the 6.3 kilohertz. That is your message frequency. Then obviously what will happen to your bandwidth? The new bandwidth. The case B is bandwidth dash is 2 times beta plus 1. There is no change. But whereas the message frequency is going to change by how much? 3 times, which is equivalent to 34 2s are 68, 68 into 6.3 kilohertz. You can simplify this to arrive at your answer. Okay, answer will be there in kilohertz. That's it, student. This is how the problem may be given. You need to observe the relationship of the beta p and beta the modulation index on the frequency and phase sensitivities, and the amplitude of the message and the frequency of the message, and the problem may be twisted in different manners so that you may be arriving at your proper answers. That's it related to the power bandwidth calculations. Then next we are going to see the transmission efficiency of the frequency modulation. You know the wideband FM signal. Now here the transmission efficiency is defined like this: the ratio of the sideband power to the total power. Maybe in 200 you may be keeping, and sideband power here refers to the power subtracted from the carrier, power at carrier frequency. Now what are the powers at carrier frequencies? All the calculations has been given to you here very beautifully. For n equal to 0, it will become AC 0 beta cos 2 pi fct, the fc plus 0 fmt. That's why the power will become how much? The amplitude of the cosine is AC 0 beta by, then RMS value will become AC 0 beta by root 2. Square of the RMS value is the power at carrier frequency. Then when n equal to n, power at the first USB, whenever n equal to 1. Whenever n equal to minus 1, it will become Fc plus minus 1 times Fm. That's why this is called as the power in lower sideband, which is AC 0 minus 1 beta square by 2. Now there is another thing in the FM, that is for certain values of beta, your Z0 beta is going to get 0. Whenever Z0 beta is going to get 0, then the power at carrier frequency, which is given by PC, sometimes may be 0, and this efficiency, transmission efficiency, you may be writing it like this: 1 minus power at carrier frequency is how much? Z0 beta square, then AC square by 2, AC square by 2 will get cancelled, obviously. Why? Because total power is AC square by 2. Then your transmission efficiency may be related to your Bessel coefficient, 1 minus Z0 beta square by 1 minus Z0 beta square of the Z0 beta. Means at these eigenvalues, what is happening to the transmission efficiency? Transmission efficiency is becoming 100%, or the total power whatever you are transmitting, it is just going through only sidebands. Means your carrier is not at all carrying any power. Okay, that's why these kind of values are called as eigenvalues, and those values of beta, certain values are given here. Those are 2.4, 5.5, 8.8, 11.9. These are all the beta, the modulation index values for which your Z0 beta, means your power at carrier frequency is becoming 0, or the power content at the carrier frequency is 0. These are called as eigenvalues. Now we will solve a problem on these eigenvalues for our better understanding. Now take a look at this problem. Here there is a message signal given to you, and in this message xt is given by 3 cos 2 pi fm into t. Now from this thing, in the solution you can write the amplitude of the message is how much? 3. The message signal mt, you may be writing it is your xt, both are one and the same, which is 3 cos 2 pi fm into t, and message frequency is not mentioned any value here for now. No, it is gradually increased till 1 kilohertz. Means it is told that your FM is 1 kilohertz at one instant of time. And what is the condition? To make the power at carrier frequency 0. Means it is given to you that you're trying to make your Z naught beta. Beta is how much here? First value. You're trying to make your beta as 2.4. Why? Because your first eigenvalue is how much? 2.4. The eigenvalue concepts. And the same thing I am mentioning here, the different values of beta for which J naught beta are 0 or 2.4, maybe 5.5. Then the other value 8.8, 11.9, something like this. Now, when the power at carrier frequency will be 0, whenever your beta becomes 2.4. When your beta becomes 2.4, what is the relationship of your beta? Beta is the ratio of the frequency deviation to message frequency. Now, frequency deviation means kf times the amplitude of message till your message frequency. You know about your message frequency, you know about the amplitude of message. Can you determine your kf from here? You can arrive at your kf like this. Kf is beta times the message frequency by the amplitude of the message, or in the current case you can arrive at one thing, that is beta is 2.4, that 2.4 times the message frequency is 1 kilohertz by amplitude of message is 3, then your kf will become equivalent to how much? That is 0.8 kilohertz, or maybe your kf is a constant which is 800 hertz. 0.8 kilohertz means how much? 800 hertz. Now what is given here, the other thing means find the frequency sensitivity, which you find out already. Frequency sensitivity, that is what you require to find. The first one, find the frequency sensitivity. You had already found out 800 hertz per volt. Sorry, the units, what are the units here? Frequency sensitivity, the units are hertz per volt. Hertz per volt. Then now they are fixing FM at 1 kilohertz. They are fixing FM at 1 kilohertz. Now they are asking you what? Find the amplitude of message for making the carrier amplitude 0 for the second time. Second time means what value? Your beta becoming 5.5. Now KF is fixed. KF is fixed. Then you are trying to vary what? AM is going to get varied. Then what is the other thing which is fixed? FM is fixed. I think yes. FM is 1 kilohertz. Find the amplitude of message signal for making, for fixing FM at 1 kilohertz. Means your beta dash should be equivalent to how much? Your new beta dash should be equivalent to 5.5. In this case, what it is equivalent to? It is equivalent to how much? Your new values. KF times the new message amplitude, that is AM dash, by the same old frequency FM. KF is how much? 800. Then AM dash is what you need to find. Then your message frequency is 1 kilohertz. Now how can you arrive at your AM dash here, students? You can arrive at your AM dash like this. Your AM dash, which is your new message amplitude, is 5500 divided by 800, which upon simplification 55 by 8, maybe this may be 8 sevens are 48, 8 eights are 64, 8 sevens are 56. Okay, roughly 8 sevens are 56 means this is around 6. 8 6 are 48, then again 70, 8 eights are 64, then again 6 you are getting, 8 sevens are 56, then again 40 you are getting, yeah, 6.875. that is in terms of volts. That is your new amplitude of the message, 6.875. This is how you need to arrive at the solution. Now let us go and see what are the different generation methods for FM. Our last two topics are generation and detection of FM, and then superheated and receiver. Very simply we will be going. Then here there will be a variable capacitor, fixed capacitor, inductance, and you know the frequency is given by this equation, 1 by 2 pi root L equivalent into C equivalent. Here the two C's are in parallel, that's why you can write C naught plus CV, that is your C equivalent. Whenever your CV is varying with the help of a message signal, L, C naught are constant, that's why you can vary different oscillations, different outputs. Okay, that's it related to the direct or the parameter variation method. Then going to the next method of generation, which is very important for you, that is the indirect method or the Armstrong method, which is invented by the scientist Armstrong. Now in this method, What are the things means? You're having your message signal empty, which will be passed through a narrowband FM generator. There will be two local oscillators. One may be the carrier frequency 1, the other local frequency may be providing you carrier frequency 2. There are two multipliers having multiplicity N1 and N2. There is a mixer. What is the role of this mixer? What is the role of each and every other things? We will be seeing in our next slide. Now, in this generation of FM, for the indirect method, you are going to study the Armstrong method as discussed in the last slide. Now, coming to here, you are having two blocks, frequency multiplier and mixer. You have already seen what is narrowband FM. That's why no need to discuss about that. But you should know, understand what is this frequency multiplier role and what is the role of this mixer. Mixer you might have already seen in AM, super heterodyne receiver, which you will be seeing here also now. Now, coming to the frequency multiplier, if you are given with a multiplier block of multiplicity n, whose input parameters are the carrier frequency Fc, frequency deviation del f, modulation index beta, and message frequency Fm, the output parameters will become like this. Now here I am trying to mention you what are these. Fc is the carrier frequency before giving to the multiplier. Then del f is a frequency deviation, freq deviation I am mentioning here. Beta is the modulation index for the case of the frequency modulation or the depth of modulation. Fm is a message frequency. Now how all these things are going to vary whenever you pass it through a multiplier means simply only there is change in the carrier frequency and frequency deviation and beta. Why means you already know your FM equation. Your FM equation is this one, that is AC cos of 2 pi times FCT plus beta times sine 2 pi FM into T. Now whenever you are passing through a multiplier, what is happening means your multiplier is not at all changing the amplitude, it is changing only the this part and this part. If you observe, FC is becoming NFC, beta is becoming N beta, then obviously since there is no change in message frequency remains constant, FC becomes NFC, beta becomes N beta, then obviously what should happen, since beta is the ratio of frequency deviation to message frequency, if there is no change in message frequency, obviously what should happen, the change in this del f should be represented by the change in the beta. That's why here beta is also going to get changed, means your del f frequency deviation is also going to get changed. Hope everybody able to understand why this carrier frequency and frequency deviation and modulation index are changing. Why not message frequency? Why? Because message frequency is there inside sine term, which won't get affected whenever you are passing your FM signal through a frequency multiplier. This is one of the important funda. Then the next funda is mixer. First, suppose whenever you are passing any signal having frequency Fc through a mixer, whose other input being a local oscillator frequency, where LO stands for local oscillator, which will generate the certain three different frequencies. Here what it will do means the output of a mixer in general is the local oscillator frequency. If it is greater than the carrier frequency, it is FLO plus or minus FC. Most of the cases, what is the output you are going to treat is this one, FLO minus FC. Why? Because you will be trying to choose your mixer as down converter. What is the meaning of down converter? Means most of the cases it is trying to subtract both the local oscillator and carrier frequency, assuming that local oscillator frequency is greater than the carrier frequency. But anyway, here also there is no change in frequency deviation, which is represented with green here. There is no change in frequency deviation. Okay, whenever this green parameters refers to what, there is no change. Here also there is no change. Means whenever you are passing your signal through a frequency multiplier, there is no change in message frequency. Whenever you are passing your signal through a down converter, there is no change in frequency deviation, either beta or frequency. All these parameters are going to same. Only there is change in the carrier frequency, which is going to get down converted by certain amount. What is the down converted value? The down converted value is this one, the local oscillator value minus the carrier frequency. That's about the basic funda. Now we will be trying to solve a problem on these fundamentals. Now for the below figure, calculate the frequency of the oscillator and the output frequency deviation of the FM modulator. This is an FM modulator given to you, and clearly from here you can arrive at certain things. The message frequency is given to you as, the first carrier frequency is given to you as FC1 as maybe 100 kilohertz. Yes, that is your initial carrier frequency, that is a narrowband FM. Then initial frequency deviation del f1 is 10 Hz, which is very low. Why? Because that is narrowband FM. Obviously beta 1 will be 10 by 50. If not given in the problem, you should be assuming it as narrowband. Okay, that's a narrowband signal as narrowband FM. These are all the assumptions what you need to make by looking at the problem. Then here, anyway, let us not worry too much. There are two multipliers here, 120 and 50. Means your N1 is 120, your N2 is 50 here. Then there is a local oscillator. Now if it is getting 120, what will happen here? If it is multiplied with 120, obviously here it will become how much? 12 megahertz or not? Simple reason is 120 times 100 kilohertz is 12 megahertz. Then what will happen to the frequency deviation? 10 times this will become 1200, or I may be writing it as 1.2, sorry, here 1.2 kilohertz. That is my frequency deviation. New frequency deviation del f dash, new carrier frequency, maybe I may be representing it as f dash here. The current case, yeah. Then it is passing through a mixer. Now you have seen what will happen. What is the role of a mixer? What it will do? It will try to take the difference between these two. That may be, for suppose FLO, you assume FLO minus 12 in terms of megahertz only you try to take. Obviously second local oscillator frequency will be there in megahertz. There is no change in frequency deviation, that is del f dash is 1.2 kilohertz obviously. Now what is happening to your output frequency deviation del f? Your del f is becoming how much? Obviously you can simply write n1 times n2 times your initial del f. Okay, the initial del f, which may be del f1. Okay, this is del f1. Here obviously you can write it as 120 into 50 into 10, which may be, this is 60, then again 2 zeros, 3 zeros here, 3 zeros means kilohertz. Your final frequency deviation is 60 kilohertz, that is 60 kilohertz, which you can arrive. And the other thing, what is asked to you find? You have been asked to find what? You have been asked to find the local oscillator frequency. Now here carrier frequency is known, means what should happen to this frequency here, FC? This FC should be equivalent to 50 times of FLO minus 12. Okay, that is 98.1. From this you can simply calculate what will happen. That is 9.81 by 5 plus 12 is your local oscillator frequency. And if you can calculate this, you will be getting it 9.81 by 5 roughly 2, then 12 roughly 14, you will be getting roughly 14. Okay, you try to calculate with respect to the 9.81 by 5 how much. Okay, 1.9 something you will be getting, 1.9 plus 12, 13.9. This is how the problem on the Armstrong method, or the problem based on the concept of frequency multipliers and mixer may be given. Sometimes you will be given with all other values. You may be asked to find this N1 and N2. N1 here is 120, N2 is 50. Okay, different varieties of questions may be given. Now going to the next one, the problem 6 here. Let us try to quickly solve this. A device with an input AT and Y output BT is characterized by BT is A square of T. Means here you have been given BT is A square of T. Then FM signal with a frequency deviation. Okay. For this signal, means A of T is what? A of T is an FM signal. Means you may be mentioning it like this. A of T is an FM signal. And here, what are the different things given to you? The frequency deviation of the FM is 70 kilohertz. Then the baseband signal bandwidth means message frequency is 2 kilohertz. Now it is applied to this device. Now they are asking you what means. Okay, it is just simply like this. We can arrive at the whole thing. There is a frequency multiplier with multiplicity n, and the initial frequency, okay, is 2 kilohertz. Then the frequency deviation is 70 kilohertz. That's what they have given to you here. Then This into 2 means into square. It is squaring device, means into 2. You can take it as into 2 simply. Now they are asking you what? Bandwidth of the output signal. Now for bandwidth means obviously it depends on which parameter. It depends on the frequency deviation. What is happening to the final frequency deviation here? It is becoming 2 times of the old frequency deviation or not? Obviously. Then what is the 2 times of the old frequency? There is no change in FM. FM dash is remaining same. That's why from our concept you can see that FM is 2 kilohertz. There is no change here. But what is happening? This is 2 kilohertz. You can mention here as 2. The LF is going to get changed by how much? 2 times 70, that is 140 kilohertz. Then the other thing here is, you know the relationship of modulation index. What is modulation index? Modulation index is beta is the ratio of frequency deviation to message frequency. Then obviously beta dash will become how much? Del f dash to message frequency. That's why here if you want to calculate the bandwidth of the output signal, how to determine the bandwidth? The bandwidth, you know that bandwidth is equivalent to output signal. Bandwidth dash is equivalent to 2 times del f dash plus fm, which is del f dash is becoming how much? 140 kilohertz. Message frequency is how much? 2. This entire thing is there in kilohertz. Then 142 times 2 is 284, I think. Yes, 284 kilohertz. That's why this answer is here is 284. 284 kilohertz. 284. New bandwidth is 284 kilohertz. Spacing between the spectral components. The spacing between the spectral component is how much? That is your message frequency FM. That's why there is no change in that one. Okay. This is how another variety of problem on indirect method may be given to you. Then going to the detection of the FM, we are arriving at the end of our module. Discriminator or the frequency discriminator, it will be told. The simple block is looking like this. When you should apply your modulated signal, FM modulated signal, pass it through a differentiator to arrive at certain signal S star of t. What is this? We will be seeing. Then you hear what you are doing means you are trying to convert your FM signal with the help of differentiator to a kind of AM signal. Then you are trying to use the diode detector or the envelope detector, okay, which is giving you your detected output. Envelope detector, what you have studied in your AM module. Okay, there will be so many rules like this. Okay. Okay, 1 by RS into C should be frequency, should be lying between 1 by RL into C. These are what you have seen in your earlier module. Okay. Then now how this differentiator is converting FM signal to AM signal, we'll see now. You know your FM signal AC cos 2 pi fct plus 2 pi kf integral m of tau d tau. Then differentiation means what? Your differentiation means what it is doing? It is just doing ds of t by dt. It's not doing any other thing. Now whenever you take the differentiation of cos, it is minus AC sine. Then inside you are having 2 pi fct. Differentiation of 2 pi fct is how much? 2 pi fc. Sorry, there is no t here. Sorry, you may remove this t. There is a small minor error here. 2 pi fc. Then 2 pi kf. Differentiation of integration will become same, m of t. Then means minus AC sine of theta. Then again the differentiation of theta is 2 pi fc. Differentiation of dt is 1. Then 2 pi kf integral. Differentiation of integral mt is mt. Now if you know about the envelope detector, what it is trying to do, it is trying to take the envelope of this as conjugate of t, which is your differentiator output. Now from our concept, you know that this represents the envelope part. This represents the envelope of the envelope detector, okay, which is AC mod of 2 pi fc. Sorry, this is 2 pi fc plus 2 pi kf integral m of t. Okay, there is no t here. Why? Because differentiation of t with respect to t is 1. AC mod of 2 pi fc plus 2 pi kf m of t. And this v of t, if you observe this v out of t, 2 pi fc AC all are constant. It is directly proportional to what? Message signal. From this, are you able to get back your message signal or not? This is about the detection of FM. Then there are so many different varieties of detectors for FM: direct detectors and indirect detectors, slope detector, balanced slope detector, zero crossing detector will all come under direct detectors, where you will be using the basic principles of instantaneous frequency fc plus kf times m of t for differentiating your output. But whereas going to the indirect method, the phase lock loop is very famous. Here you are going to use a phase information phi t, the phase variations in the signal to detect your output message signal. Okay, and generally you know that your basic, for suppose you are having an FM signal like this is your FM signal, then what is your ideal differentiator output means, ideal discriminator output means, you know, at these points, frequency is very low, means obviously the message amplitude should be more. At this point frequency is very less, obviously the message amplitude is very less. This is the basic funda. Okay, which is your V out of t, which is your detected signal V out of t. The input signal here is an FM signal for the phase lock loop. Here phase lock loop is given here. Sometimes the problems may be coming on this, which is a combination of phase detector followed by a low pass filter followed by a DC amplifier, and in the negative feedback you are giving your output signal, detected signal VD. You are giving to what? You are giving your detected signal through a voltage controlled oscillator, which is generating another kind of FM signal. Means your VI is an FM, and this output of this V0 both are FM signals. This is both are 90 degrees out of phase. Anyway, all those things are not that much required. Okay, you can, if you want, you can go through the textbooks and read all those things. The error is the difference between the frequency of these two. One is the incoming frequency, another is the output frequency. Why? Because you are converting your output detected signal in form of frequency and you are sending it to a phase detector. The job of this phase detector is to differentiate the errors between and it to try to produce one error signal, and that error signal frequency is plus or minus. Obviously whenever you are passing two signals to a detector or a multiplier, obviously the output frequencies are getting added or subtracted, then the lowest one among those two will be selected, that is Fi minus F naught. Then the DC amplifier or the loop filter will try to eliminate this error. That error should be made equivalent to 0. Then this should be passed through a wave, and it will be continually happening like this. Anyway, for your ease of understanding, the VD can be represented as KF by KV times the message signal, where KV is the voltage sensitivity, frequency sensitivity of this voltage controlled oscillator. KF is the frequency sensitivity of your FM signal. Anyway, you can go in depth and in detail with respect to the different textbooks, but these are what are required. There are also Foster Seeley detector. Foster and Seeley both are scientists. Then again ratio detector. These are all the very old methods, but phase lock loop is even being used nowadays, which is very important. And those who are interested, they may go through the textbooks for understanding the detailed description of phase lock loop. You require the control system's thorough knowledge here for understanding this phase lock loop, what is capture range, lock range, and all other things. And coming to the last one, that is FM super heterodyne receiver. Here the broadcast range for FM is lying from 88 to 108 megahertz. Whenever you are receiving any signal 88 to 108 megahertz, there is a variable local oscillator, and the incoming signal frequency is Fs. Fs is the incoming signal frequency. Then FIF is the intermediate frequency. And what is the super heterodyne receiver means? Intermediate frequency. RF stands for radio frequency. Then LO stands for local oscillator. Local oscillator will try to generate what kind of signal? It is try to generate one kind of frequencies. Then mixer is generally a down converter, most of the cases. Not mandatory to be a down converter, it can be anything. And here the basic relationships, what you can be taking it as a notes are: the intermediate frequency for FM is the difference between the local oscillator frequency and the signal frequency, and which may be maintained until unless given in the problem, maybe roughly around 10.8 megahertz. And the image frequency, image frequency which is given by Fs dash as fs plus or minus 2 times the intermediate frequency. This depends on the range of reception. It depends on the range of operation of this RF receiver. How we will select whether it is fs plus 2 or fs minus 2 times the intermediate frequency. Okay, then the other thing is here, there is one rho parameter which is defined as the ratio of the image frequency to signal frequency minus signal frequency to image frequency, and there is another parameter called as alpha, which may be also called as image frequency rejection ratio, and alpha is defined as gain at the signal frequency to gain at the image frequency, that is alpha, which is also called as IFRR, and this is rho one parameter. Now if you know the quality factor of a circuit, that is the resonant frequency by bandwidth, or which may be given in the problem, the quality factor relationship with this. Now here how you will arrive at the image frequency rejection ratio alpha means, that is root over 1 plus, after calculating rho you do rho square q square, and here you can keep here this image frequency rejection filter, image frequency rejection you may be keeping just before the mixer. And for the frequency modulation case, the other things which you maybe need to be taking a note, or the ideal frequency deviation for FM is 75 kilohertz. The ideal bandwidth per channel is 200 kilohertz. Then the ideal intermediate frequency is 10.8 megahertz. Yeah, then this is rho, this is image frequency rejection ratio formula. This is how quality factor is dependent on resonant frequency and bandwidth. Then after arriving at the image frequency, there will be a image frequency amplifier. Then there will be different kind of FM detectors, maybe phase local loop for ease of understanding or anything. You will be having some other things also. You will be having a hard limiter here, which I am mentioning here, maybe in some color. Yes, hard limiter. You should understand what is the role of these things. Hard limiter. Then after detection there will be some other circuit called as de-emphasis circuit, which is the opposite of pre-emphasis. Okay, pre-emphasis is the boosting of the signal which will be kept at the modulator side. Then de-emphasis is boosting down of the high frequency audio signal after detection, which is used only for the frequency modulation, whereas pre-emphasis and de-emphasis are not there for the amplitude modulation. Why? Because FM is operating at high frequency band. At high frequency band you require de-emphasis at the detector. Then this is your loudspeaker. The audio proper power amplifiers are required, power and voltage amplifier, to detect your signal. This is how your problems may be arriving on image frequency. Image frequency is the ratio of local oscillator frequency and signal frequency, that is intermediate frequency, sorry. Then image frequency is signal frequency plus or minus 2 times the intermediate frequency. Then rho is calculated as fs dash by fs minus fs by fs dash. Then the image frequency rejection ratio is given by alpha, which is defined as the gain at the signal frequency to the gain at the image frequency. Why? Because you don't require image frequency. Image frequency is the thing which is one of the demerit of super heterodyne receiver, and to eliminate that one you are using one image frequency rejection filter. But the advantage here is your detector is always working on an intermediate frequency signal. That's why what is happening, you are able to stabilize your Q. Whenever your Q is stabilized, then your circuit will function better over a long range of frequencies. Okay, that's how you can improve the some of the parameters of the receiver. Fidelity you can improve, then sensitivity, selectivity also can be improved. Okay, sensitivity depends on the gain of the receiver. The more the number of blocks, the larger the gain, sensitivity is improved. Selectivity, whenever QE you are able to maintain a fixed Q, obviously selectivity is going to get improved. Then depending upon the reception range of your local oscillator and RF, this is the receiving antenna. Depending upon the synchronization, you are able to achieve the fidelity also. And that's it, students. These are the references. You may go through these textbooks, which are very standard. Communication Systems by Simon Hackin and Wheeler. This is Wheeler second edition. Then Herbert of Donald L. Schilling and Gautam Shaha by Tata McGraw edition. Then Modern Digital and Analog Communication System by B.P. Lati and Z. Ding and Gupta, going to the Oxford publications. Then Electronic Communication System by Kennedy and Davis. This is also Tata McGraw edition. Then you require some of the basics of signals and systems for drawing the spectrums and all other things, which you may refer to Simon Hackin and Vwin. This is also Willy Publishers. Then coming to the simulations or the waveforms, what I have shown you for the FM and PM, those are done from the open source software, that is the GNU Octave, which you may be using, which is a similar like MATLAB, but whereas MATLAB is a licensed version, but if you go for GNU Octave, it is an unlicensed where you can do some of the minimal simulations. Thank you all students. If you are having some doubts, you may refer to the first slide and you may contact me through my mail ID gskfet@kit.ac.in, or you may reach out to my other mail ID, that is satishkumar.gannamaneni, GANNAMANENI@gmail.com. You may reach me out here, then any of your other doubts can be further clarified. That's it students. Thank you all for going through this course. Thank you very much.